How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at 6.7 and 8 problems where we look at many electron atoms and electron configurations. All right. Explain in your own words what is meant by the Pauli exclusion principle and Hund's rule. All right, so in my own words, Pauli exclusion principle is saying that no electron can have the same 4 quantum numbers. And what that's saying really is like the electrons can't be identical, right? If we're talking about where these electrons are, they can't be in the same place. Minimally, they have to have different spins. So they can't have the same 4 quantum numbers. They can't be identical. And Hund's rule, I think of is it's like the Manners rule, in that every orbital in a sublevel gets an electron before any of them get 2. So you gotta make sure everybody gets serving first before you go back for seconds. That's just, manners. You go big Thanksgiving dinner, a bunch of people, whole family's there, and you're the first in line because you're hungry. You can grab food and you power through all that food. Guess what? You should wait till everybody's had a chance to get their first plate before you go back for seconds. What if you run out of food? That wouldn't be good. And somebody didn't eat because you had seconds. Don't be rude. All right, 28. S sublevels can hold how many electrons? Well, the S has a single box that can hold 2 electrons, 1 up, 1 down, so that's 2 electrons. P can hold, well, let's see, the P has 3 orbitals, and they each can hold 2, so they can hold a total of 6. The D sublevel has 5 orbitals, and there's 2 in each, so that's a total of 10. And the F has 7 orbitals, which, look at that, I drew it, perfect, awesome, which means they can hold 14 electrons. All right, 29. Below are examples of electron configurations. Analyze them and identify which may violate the Pauli exclusion principle, Hund's rule, or if they are acceptable. So let's take a look. Well, for A, there's, error right here. There's 2 down arrows. Well, which one does that violate? That violates the Pauli exclusion principle. So I'm going to abbreviate that as PEP. So this is violating that because these 2 electrons would have the same 4 quantum numbers. It'd be first energy level, S sublevel, the only box, the only orbital available, and then they'd both be -1/2, and that can't be possible. That's a frown face. All right, next one, let's see. We got 1s, up, down, that's good. 2s, up, up, that's a problem again, and it's the same error. Pauli exclusion principle. They would have the same 4 quantum numbers. Can't have that. C. Let's see, 1s, up, down, that's good. 2s, up, down, that's good. 2p, up, and then up. This is completely acceptable, right? That is a good diagram. All right, next one. 1s, up, down, that's good. 2s, up, down, that's good. 2p, up, down, up, up. Uh-oh, this has got a couple of violations. One, right here, that is the Pauli exclusion principle. They'd have the same 4 quantum numbers. You can't do that. And then also the fact that, hey, why doesn't this box have any electron if they both, the other 2 have 2? So it's both. So it's going to be Pauli exclusion principle and Hund's rule violation right there. Now the last one, we got up, down, that's good. Up, down, that's good. Up, down, empty. Nope, that is a Hund's rule violation because this poor fella didn't get any mac and cheese because somebody went back and got seconds before everybody got their firsts. So they were rude, all right? So don't be rude. All right, 30. Which of the following choices represent an acceptable set of quantum numbers? So remember, n can be any number. L can be from 0 to n-1. And ml can be anywhere from positive L to negative L. And ms can only be plus or minus 1/2. Those are the only 2 possibilities. So let's check. All right, well, A, we got 3, 3, -1, -1/2. There's a problem right here. This can only go up to 2, right? Because that angular momentum one should only be able to go to n-1. And if n is 3, then it should only be able to go 2, so you can't do A. All right, B, 1, 0, 0, negative 1/2. This looks pretty good, right? If I have n equals 1, then the next number can be 0, which it is, which means the next number can only be 0, which it is, and the next number can be minus 1/2. So this looks good, this smiley face. C, 1, 1, 3, 1/2. There's an error right here, right? So if n equals 1, then the next number can only be 0, which means this magnetic quantum number can only be 0 as well. You can't have it be 3. So frowny face for choice C. All right, next one, 5, 3, 4, minus 1/2. Again, if n equals 5 in this one, then the angular momentum can be up to 4, so 0 to 4, which it is, so that's okay. But then the next one can only be plus or minus whatever L was. L was 3 in this case, so it can't get to 4. All right, so it can't get to 4 because the number before it was 3, so frowny face because of this problem right here. And then E, 3, 2, 3, minus 1/2. Again, same issue as the one before it. If this number is 2, then that number can only go from plus or minus 2, and it's at 3. So error right there, no go. Frowny face. Correct answer, choice B. 31. Which of the following choices represents an acceptable set of quantum numbers? Again, same as the last problem, but this time different options. All right, this one is completely okay, so that's good because n can be any number. L can go from 0 up to n minus 1. ML can be plus or minus L, whatever number was before it, and then MS can only be plus or minus 1/2. So, oh hey, look, this looks okay because it's 2, which means this can be anywhere from 0 to 1, which it is, which means if it's 0, then this can only be 0, so that's good, and minus 1/2. This is looking good. This one right here should jump out at you. Hey, that can't be 0. It's got to be plus or minus 1/2, so definitely not B. Frowny face for B. All right, C, we got 3, 3, This 3 right here, if n equals 3, then L can only be up to 2. And it can't be 3, so definitely not C. Frowny face for C. All right, D, we got 4, 0, 2, Well, if this is 0, if L equals 0, then ML can only be 0. It can't be 2, so, the problem there, frowny face for D, can't be D. All right, 1, 0, 1, same issue. If L equals 0, then ML can only equal 0 as well, because it's plus or minus 0, it's just 0. So it can't be 1, frowny face for E. Correct answer is A. 32, draw the orbital diagram for an atom of nitrogen in the ground state. So nitrogen has a total of 7 electrons, right? Its configuration is going to be 1s2, 2s2, 2p5, no, 3. Oops, there we go. So that is all the electrons. And if you don't remember how you're supposed to fill the electrons, you can remember the diagonal rule and just go, all right, well, let me write out all this stuff, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and then you fill it diagonally. You go, all right, well, s can hold 2, so all those are 2. p's can hold 6, and d's can hold 10, and F can hold 14. So you fill them in. If I have 7 electrons a place, I start diagonally. I got 1s2. I have 5 more. Then I go to 2s2. That's 2 more, so I have 3 more left. So I'm going to go to 2p, and then I'm going to fill in just 3 out of the 6. So the orbital diagram is going to be showing the boxes. So I do 1s, and then I draw a box, 2 electrons, so up and then down. 2s, 1 box again, because it's just the s sublevel, up and then down. Now the 2p3, I know the p sublevel has 3 boxes, so boom. And how do I fill them in? Well, remember Hund's rule, everybody gets 1 electron before anybody gets 2. So you fill it in like this, 1, 2, 3. And that's it. You're done. You've placed all your electrons. There's your final answer. Be happy about it. All right, 33 says draw an orbital diagram for nitrogen that violates the Hund's rule. So there's going to be a bunch of ways that you can do this, but let's start with drawing out the boxes. So I know it's going to be 1s2, I got 2s2, and then I got 2p3, and the p has 3 boxes, so 1, 2, 3. There we go. All right. Well, I am going to keep all this the same because that's not where I'm going to violate Hund's rule. If I have to place 3 electrons in this last sublevel, and I want to violate Hund's rule, remember the Hund's rule is the manners rule. You got to make sure everybody gets 1 before anybody gets 2. So if I'm violating that, I got to give 2 to one of these orbitals before I give 1 to any of the other boxes. So I can do this, up, down, and then up. Now I placed my 3 electrons, and this box doesn't have any. You violated Hund's rule. So that's probably the easiest possible answer. There are other ones though. And 34. What element has the ground state configuration of Kr 5s1 4d4? So you might be saying, how's the ground state if the 5s only has 1 electron? That happens sometimes. So when you get a problem like this, don't freak out and worry about it. All you really got to do is go, all right, well, it's an element and its ground state. It's not an ion. So it's going to be Kr, and then how many more electrons? Well, I got 1 and 4. So it's going to be Kr plus 5 more electrons, which means it has 5 more protons. So I'm going to find Kr right here. You go, all right, well, let me count 5 more. 1, 2, 3, 4, 5. It's going to be NB, right? That's it. That's how you do that. Next problem, similar but different. It says argon 4s2 3d10 4p4 is the electron configuration of an atom in of blank in the ground state. So I'm going to go, all right, well, again, same thing. Argon, has an atomic number 18, and that's how you draw an 8. And then there's 4s2 3d10 4p4. So I'm really adding 2 and 10 and 4. And I get a total new number of, I can't do that math, 34. So I'm really asking what element has atomic number 34 or comes up 16 after argon. So I can just go, all right, that is going to be selenium, Se. That's how you do that, right? You can count it too if you want it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There you go. That's how you do that. 36, last one for the section. Give the abbreviated electron configuration for an atom of fluorine in the ground state. So I'm talking about fluorine in the ground state. And the way you do this is you go, all right, find the element that you're interested in, find the previous noble gas, so you know that that's going to be your abbreviation. So the way that I do this, I remember that this is the S block, this is the D block, and then this is the P block. And that's going to tell me where these electrons are going. So I got to go, all right, I got helium, and then what? Well, I'm in the second energy level, so I know it's going to be 2, and I'm in the S block right here, so it's going to be S, which holds a max of 2. So I go 1, 2, done, that's full. Now I got to jump over this big gap and go to the P. Again, second energy level, this time in the P block, so it's a P sublevel, and I got to go 1, 2, 3, 4, 5. So it's going to be 2p5, and that is my abbreviated electron configuration. So I hope you found that helpful. I'll see you in class. Goodbye.